All right, this is the first video in a series of videos I'm going to make on designing a PCB or a printed circuit board. I'm going to be using Altium Circuitmaker. I'm going to do this in probably a few main videos, and then I'm going to have a bunch of shorter videos that are offshoots of it that get a lot more detail about it. So if you just want to make a quick board and just crank out a circuit, just watch the main ones. All the other ones, if you want to get more in detail about various aspects of actually how to get Circuitmaker to do nice things for you, how to get it to work properly, and get more on a professional level of using the software, then you can watch the following sub videos. Now, just in case you're unaware, the PCBs are pretty much everywhere. You're probably surrounded by 4 or 5 of them at any one point. They're in everything from phones, computers, watches, of course, but they're also in things like some shoes. They're in pregnancy tests, appliances, USB drives, power tools, and most LED light bulbs have 1 or 2 PCBs. Now, before we get too much into it, think of a PCB as basically a substrate or the scaffolding upon which you build an electric circuit. It has a bunch of wires and traces that are built into the board that connect all the components. It has connectors on it that will connect to the power sources and to the outside world. So just a little bit of fun background that PCBs are not the only way to build a circuit. Now, before printed circuit boards, there is something called the point-to-point soldering. So you would build the actual circuit by soldering them together. You can see this is the insides of a Keithley 225 current source. This is the control knob. So you turn the knob and it selects the current ranges that you want to output. So by turning the knob, you're actually reconfiguring the circuit. So if you look a little closer, you can see that there are several resistors connected together. There's diodes. And so this is basically a reconfiguring circuit as you turn a knob. So the disadvantage of this is that it takes a significant amount of time. This has to be done by hand, and it's expensive. So a lot of this, you just won't see things like this in modern equipment anymore. Another way to build electrical circuits is the ubiquitous solderless breadboard. I think anybody who's gotten into electronics a little bit has probably experienced with the solderless breadboard. Now, the advantage of this is that you can build and rebuild the circuit quickly, and this is great for prototyping. The downside, however, is that as you can see, there is a crap ton of wires everywhere. And this is a relatively simple circuit, but it gets messy very quickly. Now, another solution that is to use prototyping boards. These are boards that have a grid of solder pads. So you can see none of these pads are connected to each other. It's just a large amount of holes in solder pads. So the ones here on the right is, you can see it's a nice throwback from Radio Shack. Now, the advantage of these is that you have a large number of holes that see all of these parts are something that you can solder a through-hole component into, and then you connect the wires. So the advantage of this over a breadboard is that the circuit is fairly permanent. You can obviously desolder it or cut wires, whatever, but it's just these prototyping boards are just a lot of holes. And Pac-Man will just suddenly appear and want to eat them. So it's up to you to actually connect the circuit together with wires. So here's an example of a circuit that I built a number of years ago. This is the circuit on the left that you see on the top of, and on the right we see the bottom. So you can see there's significantly fewer wires than if I built this on a breadboard, but then there's also, it's time consuming. You have to cut all the wires to length, you have to measure them, strip them, put them in the holes, solder them together. And if you can see on the left, it's actually, it can get messy. A lot of times it's easy just to create solder blobs on the bottom. To connect the wires, to connect them instead of using wires. So there's another way you can make a circuit. You can actually make your own homemade printed circuit boards. Now you can see the one here on the bottom right is one that I built with basically using a Sharpie marker and some ferric chloride. So that one is essentially you create a mask of the lines and the traces that you want to keep. And then you immerse it into ferric chloride for, it could be anywhere between 10 and 20 minutes. and then it dissolves everything that is not covered by the mask or the Sharpie marker. And this other one on the top, that is built using a PCB router. So it's a step in the direction of much more professional looking. So this is, all the traces are going to be nice and neat. You can make much finer traces than you could by just drawing with a Sharpie marker. But the disadvantage of that is that, it requires a piece of equipment. So one of the things to keep in mind is that with the PCB router, you're removing the material mechanically, whereas with using the Sharpie marker or one of the other techniques I'm going to show you shortly is that, it needs chemical etching to remove the traces that to remove the copper that you don't want. So this is an example of a circuit I built. So this is again using the Sharpie method. So you can see the drawing of the circuit on the left. This is actually after I've immersed it in ferric chloride. You can see a little bit where let's see over here, you can see I've got the kind of the top diagram of a transistor. So this is just a transistor tester. And on the right, you can see I've cleaned up the Sharpie marker just using some acetone. Now, if we look a little bit closer, you can see some of the disadvantage of using the Sharpie marker method. You can see there's so as you're drawing with a Sharpie marker, especially on a smooth surface like copper, it's not going to fully cover the trace. Whenever you draw black, you'll see like little holes and lines. I like to call it the quick and dirty method. If you just need to build a circuit and you just want to crank it out real fast, it doesn't need to look super professional. It's an easy way to do it, but again, it requires access to the ferric chloride. You have to dispose of it properly, and it could be messy. Now, there are two other methods that are often used, utilizes transparencies. One of them is the toner transfer. So you use a laser printer to deposit the image, the actual size image of your printed circuit board design of all the traces and the footprint, the solder pads and footprints, and then you actually print it in a inverse. So you print it a mirror image of it. Then you flip it over top the copper clad board, and then you attempt to remelt the ink. So the ink in a laser printer is a thermal set epoxy. And so the idea is that you take an iron and you put it over top. You try to heat up the transparency until the point where the toner remelts, and hopefully it deposits it onto the copper clad board. Another one is actually, this is going to be a little bit better, but again, it requires a bit more. So this is a photo developing. So again, it uses a transparency. You print the actual image you want made on the board, and it uses a lot of the same chemicals as photo developing, and then you're developing it just like a photo. So when you develop it as a photo, it leaves the image of the traces that you want to keep, and so that provides a mask that when you dip it in acid again, the ferric chloride acid, that it will dissolve all the copper that's not exposed. Now, other methods that I've heard of and haven't used myself, but include a laser etching. So you use some of these laser etchers that are becoming relatively inexpensive, and to make the circuit pattern that onto the board itself. Another one that's becoming that's fairly new is 3D printing. So this will actually extrude conductive ink onto a board. I'm not entirely sure how well it works, but the nice thing about that is that it's fairly quickly developed. There's no chemicals that are involved. The downside is that you might, I'm not too sure how much resistance or how much impedance that the conductive ink that they use will actually cause. So it might not make the best printed circuit board, but it's certainly an interesting development. Now, ultimately, what we want to get to is the professionally made printed circuit board. So this is a collection of small boards that I've made, some recently. So up in the top left, this is a small robot sensor that I'm using. These are two photoreflective sensors. At the bottom, this is a motor driver. You can also, with the professionally made boards, you can build custom shapes. So this is a programming adapter, and you can build even small little breakout boards. So this is one I have. It's just a generic SOT236 footprint. And so this one I have a gate driver soldered onto it. So you can actually take a surface mount component and put it in a printed circuit board, just like as if it was a through-hole component. And you can also build your own custom microcontroller. So of course this is my own custom-made Arduino. Now before we get into, I think it's also really good to know what the parts of a PCB and some of the terminology are. It's not a whole lot, but it's, once we start getting into the videos and I start saying some of these words, that you have a better idea of what they are. One of the most important things of a very professionally made circuit board is the solder mask. So this one in particular is green. They have some companies offer various colors. The idea of the solder mask is that it protects everything that doesn't need to be soldered. So these are some solder pads. So it protects the traces. So these aren't actually green. This is the semi-transparent solder mask that's over top of it. It protects the board from corrosion. This is actually copper and it will oxidize over time. It also, especially when you're soldering small components such as this little device up here, is that it repels the solder. So it's helps to prevent the solder from going where it shouldn't go. We can get more into that in later videos. And there's also through-hole components. So this particular board is a combination of surface mount and through-hole components. The through-hole is cleverly named because the component is a leaded component, and the terminals go through a hole. So here we have a magnified image of it, so you can actually see the hole goes through nicely. So the part that goes around it is referred to as the annular ring. So here we can see a little bit better the solder mask, which is the green part, and the exposed metal. This is called the solder pad, and this is obviously the hole that goes through it, that the lead passes through. Now the white part is, we'll get into just a second, this is the silk screen layer, and that's just printed on top of the solder mask. This has no electrical function. It just helps you identify what parts are what goes where, and particularly the orientation. Now here we have traces are basically all the wires on the printed circuit board. So this does all the work of moving electrical signals and power from components all around. And here on this board we can see we've got traces of different widths. So this one is going to carry a higher current. This is going to carry all the power. And then the thinner trace is going to be more your signal wires. So each of these are LEDs. They only need to carry 20 milliamps, whereas this one might need to carry several hundred milliamps. And here's another part. So vias are very important. They are ways to go from one side of the board to another. So you can have, where the through hole, you can have a plated through hole. That means there's metal on the inside of the hole, on the inside of the walls, and it passes the signal from one side of the board to another. Now, a via is made specifically to take signal, also power, can from one side of a board or from one layer of a board to another. Now, vias, when you get into the signal integrity, they get to be very complicated. Signal integrity has to do with everything that's high speed, so 10, certainly 100 megahertz and above, you have to consider signal integrity. I highly recommend taking a class on that. It's a very interesting topic. The silk screen, as I just mentioned before, it's just the white material that's printed on top. One of the things you always want to have is make sure that you identify what components are what. So I always like to throw in some silk screen, so when I make the components, I know what they are. And we also have solder pads. So this refers to surface mount components. So these are actually fairly large components, relatively speaking. One of the things that's really useful, especially when it comes to devices with an orientation, like you can see up here, this particular package is 4-sided, but if you don't know which pin is pin number 1, you don't know, it can go in any one of 4 orientations. So this has a little dot that tells you which one is pin 1. So on the package, there will also be a dot or some other indicator to say this is pin 1, and they go around counterclockwise. So you can also add some of your or other devices that have orientations, such as the LEDs. So here you can see the anode side and the cathode side of the diode, so that your circuit actually works. All right, this is just to illustrate a little bit more of how the circuit board functions. So you can see all this is, I have this is illuminated from behind, so you can see all the through hole, all the light goes through the parts. But what's even more interesting, you can see this light green is the substrate and the solder mask only, and the dark green is where there's copper. So it's obviously far less translucent. It's actually fairly opaque. Now this is just a 2-layer board. You can't really see much. There might be some traces. This might be a trace or two that goes behind on the other side. But the majority of this board, of these traces, are on the top layer, the layer we're looking at. Now, some of the reasons that you would want to go through the effort of learning how to make your own printed circuit board, or how to design them, I should say, is that they're extremely cheap. They used to be, even 5-10 years ago, it would be difficult to find one for less than $100. Now you can buy them from various companies for a couple of bucks, and you get maybe 10, depending on the size. They're quickly made anymore. I can order one from a company in China, and in a week later, it's in my hand. The quality is fairly good. Obviously, if you want higher quality, you're going to have to pay a little bit more. You can get them built on various substrates. Usually the standard is FR4. There's all kinds of other exotic materials. You can have a PCB with aluminum backing to it. So if you're building something that needs to really conduct a lot of heat away, you would use that. It has the solder mask, has the silk screen. You can build them in custom shapes easily. They're much more reliably made for using tiny surface mount components. Did I mention they're also really cheap? They're boards, I think I purchased maybe 20 of these. I maybe spent $10 on them all, and then shipping is maybe 10 or 15 bucks. So unless I continue rambling, let's actually take a little bit of time, and we're going to fly through this PCB so we can see a little bit more of the detail up front. To do that, I'm actually going to use the software. We're just going to dive right into it, and then we'll get into it in more detail later. All right, here's the same board that we were looking at. Now this is the 2D view, so if I want to switch to 3D, all I have to do is press the 3 button, then the rest of the parts should populate. This is actually a different project, so there's no part for it. That's why I put the little silk screen on there, so you can actually know what the orientation is. So all I'm going to do is press Shift and hold it down. Then I'm going to press the right mouse button key, or rather the right arrow key. Then we can rotate that around. We're actually going to zoom in. So I'm pressing and holding the control and the scroll wheel up. So you can see in between, so now I'm just using the scroll wheel to go up and down. You can see the 2 different layers. So if I move in close, so it's not going to show the actual substrate, the material. So this is why it looks like, we're looking through. All these tubes are going to either be vias or through parts of the through-hole component. So this is one of the switches, and so if I fly in closely, you can see the trace going to the device. So rotate it around. So you can fly into the board. And if you look up, you can see, oops. You can see all the traces. That's going to be on the top layer. So here I am zoomed in. These are pins that are connected to ground. So you can see these thermal relief traces are connected to the rest of the ground plane. So if I fly underneath, all right, so this is the ground plane. You can see the thermal leafs on the bottom side, and they're connected to, this is going to be the plating of the through hole. So all of what we don't see is the substrate, and it's connected to the bottom layer via a pad. All right, so here we are over at the voltage regulation section of the board. This is, you can see the connector for the power in. This is the switch mode regulators, this is a little inductor, and this is the vias to the voltage out. And this is just a little via over here that's connected to the ground plane. And this is a 2x5 connector. So if I start flying through, so I can rotate it down, and actually enter into the substrate of the board. You can see those. So zoom in. So here are the 10 connectors for the 10 connector pin. And these are the, so we're underneath the voltage regulator. See all the traces coming out from the solder pads. These are the thermal vias, so these don't actually conduct any electricity or current, but they're used to pull out any thermal energy. Yep, this is our ground via. So here I'm actually connecting something else on the other side to ground. So this is kind of a fun picture. You can see how this must be probably an isolated component of the regulator. Probably was isolated off from the ground. And so here I'm dropping a via underneath, and then I'm connecting it to the other side so I can connect it to the ground plane that's above. And so it's interesting to see it from underneath. So now we've got the top layer above us and the bottom layer below us. And this is the 2x5 connector. And if we look at and go above, we can see the 3D model of the connector. You can see the terminals going through, or we can see the leads going through. And if I go down to the bottom board, you can see those traces going through the hole. And you can see the model's not quite centered right, but it's close enough. But it's just, I think it's interesting to see the insides of the board. Yeah, here we have a board that's 4 layers. So again, we're gonna press number 3. Let's go to 3D view. So one of the things that you should note, so you can see the 4 layers. So here's the top layer, here's the next layer down, here's the other layer, and here's the bottom layer. You'll notice that they're not symmetrically spaced. So when the manufacturers build this, they take one board that's double layer, and they basically sandwich 2 thin single layer boards on top. We can do the same thing. We can fly through. This is all the through-hole connectors that will be for the pin headers that connect it to the board we were just looking at. And so one of these, I forget which one, they're both the power plane, so one of them is positive, the other is ground, I forget which is which. And so it's a way to connect something on the top layer to the ground plane or the power plane without having to run traces all around. Now we can start flying through the board. You can see, yeah. So here, this is just another thermal relief. So this is something that's going through this power plane. I believe this is the ground layer, and I think this is the positive rail. So here I'm going through, it's got a cutout from the power plane so it doesn't short through, and then it travels through and connects to the power or the ground plane. Yeah, here's another good perspective where we can see the 4 layers distinctly. Now we've got the top layer, you can see the solder mask layer and the silk screen layer. Now this is going to be the positive rail, this is going to be the ground plane, and here we have the bottom solder mask and the bottom layer. Alright, so this is the end of the introduction. The next videos we're actually going to start going through the process of designing a circuit. How do we actually go through and build a printed circuit board? Alright, I'll see you there.